So this is the last lesson of the first semester, with the first semester really being the semester that we deal with derivatives. And I saved this for the last lesson because, and I could have done it before today, because it's a really just simple but super important concept that if you take anything away from the first half of the class, it's this. If you want to find maxes or mins, take the derivative, set it equal to 0. So simple, but so important. On the AP test, if you're not sure what to do, take the derivative, set it equal to 0. You might be doing the right thing. It's done so much. Moving forward into other calculus classes, we will find that, finding maxes and mins are very, very important, and we will be taking the derivative and setting it equal to 0 to find it, okay? Now, we will be talking about absolute extrema, which is our overall maxes and mins, and we'll also be talking about optimization, which is finding a max value or a min value of some, real world situation. But it's all about finding maxes and mins. Let's review first how to find relative extrema. We've already done this. It started with taking the derivative and setting it equal to 0. Yes, we also are concerned with when our derivative could be undefined, but we will find that for most functions this is unnecessary. We won't have sharp points for those situations. And we just take the derivative, factor to solve, and we have possible maxes and mins. And what we do is we analyze the signs of our derivative by plugging test points near 0 and 2 into our simplified derivative. And we figure out that my original function f increases till 0, decreases after x equals 0, and up until x equals 2, and then increases after x equals 2, which is showing you that x equals 0 is the location of a relative max, and x equals 2 is the location of a relative min for f. Right, we've done that before. Piece of cake. Well, let's move towards not necessarily relative maxes and mins, but absolute maxes and mins. Now we got two pictures. One picture, we see we have a largest y value. It's definitively the largest y value and a smallest y value. This function right here has an absolute max, which is also at the location of a relative max. Okay, it's the overall largest value. Here, this is the overall smallest y value. This is the absolute min, which is also a relative min. But for this function, you have a relative max and min, but my function increases to the right and decreases to the left. There are no absolute maxes or mins. Okay? So what this is telling us that we don't always have absolute maxes and mins for a function on an open interval. Well, because we're trending towards infinity, so we would say like the absolute max is infinity, but that's an ever increasing number. It's more of a concept, so we can't say the absolute max is infinity. If this like trended towards a specific value, we even wouldn't say that like maybe we have like an asymptote at 50. It will never equal 50 though. So we can't even say this has an absolute max. It'll just get ever infinitely close to 50 without going over.
Okay, yeah. So I thought you meant the first
Now,
one. There you do.
the first one we definitely do. This is the largest y value. This is the smallest y value. Okay. So there may not be absolute maxes and mins on an open interval. Okay, but let's talk about a closed interval. And after we discuss the closed interval, we'll be able to talk about the extreme value theorem. So this is, one of those cubic functions that does not have an absolute max and min if we look at it from negative infinity to infinity. Well, what if I just say, let's just look from -2 to 3. And let's include the point at -2 and 3. So we use these closed brackets for a closed interval. That means we are including the values at -2 and 3. Okay. Well, all of a sudden, these trends towards infinities, we don't have to worry about. And we see we just have an absolute max, which is the location of our relative max, and an absolute min, which is the location of our relative min. Okay. Well, what if I looked at the interval from 0 to 3? Including 0 and 3. Since I'm including the point at 0, turns out my absolute max occurs at that starting point, at 0. That is the largest y value of that function on that interval. So what we find is that we have an absolute max on an endpoint. Whereas 2 is still my relative / absolute min. We call that an endpoint at x = 0. Now, if we looked at any interval anywhere, we would find that the absolute maxes and mins will always occur either at a location of a relative max or a relative min, or at an endpoint. That is the extreme value theorem. It says that on a closed interval, there will always be an absolute max and an absolute min. And going further from that is our candidates test, which kind of comes from our extreme value theorem. Extreme value theorem says we will always have an absolute max and min. The candidates test is, hey, your absolute max or min will be at either at a location of a relative max or min or at an endpoint.
So on the second interval, the one that was an endpoint is just an absolute max and an endpoint. It's not a relative max.
Not a relative max. It doesn't have a tangent slope at 0. Doesn't go from increasing to decreasing. Yep. So again, this is on a closed interval for this candidates test. The absolute max-min will occur at the location of a relative max or min or an endpoint. Okay. So let's go back to that first function, x cubed minus 3x squared plus 5, and let's find the absolute max and min for the function on the interval that is given to us from 1 to 3. Now, the candidates test, really, all you're going to have to do is compare some y values. And since we know that we're going to have our absolute max and min either at an endpoint or a relative max or min, we just really need possibly, 3 y values, the 2 endpoints and maybe 1 relative extrema. Or if we have multiple relative extrema, those couple plus the 2 endpoints. And if we just find the y values, we will know for certain that one of them will be the max, one of them will be the min. Okay? So watch how I can do that quickly. I can take the derivative, set it equal to 0, which is how we find maxes and mins. Factor to solve just like I did before. We get 0 and 2. We will only concern ourselves with 2 as it's in our interval from 1 to 3. And then I will say, okay, by the extreme value theorem, I have some candidates. Either the absolute max and min will be at 2, or it'll be at 1 or 3. 2 being my relative extrema, and 1 and 3 being our endpoints. This is the candidates test. If I find the y values of those 3, I can compare the y values and know definitively which one is the absolute max, which one will be the absolute min. Okay? It's a lot easier than sometimes than looking at the signs of your derivative and comparing them. And also, sometimes those won't help completely. So I plug in 2, I get 8 minus 12 plus 5, that's 1. I plug in 1, I get 1 minus 3 plus 5, that's 3. Plug in 3, I get 27 minus 3 times 9, which is 27 plus 5, that's 5. So by comparing our candidates, I know definitively that that would be the location of the absolute min on the interval, and this would be the location of the absolute max. Yes, Ms. Ward. Right, we're comparing the y values, not the tangent slope values. The tangent slope values are not telling me which one's higher than the other. It's the y values that are telling me. So I plug this into the original equation to compare their y values. Okay. Now, what we should still do, though, is have this idea of the signs of my first derivative in my brain, being ready to use it. Because actually, it will help us for certain situations. Now, it's important, if we're talking about an interval, we can do a signs of my first derivative with a start point and an end point, and our relative extreme in between. We know that between 2 and 3, this will be positive. Between 1 and 2, this will be negative. Now, think about this. Just by looking at this, you will know that on this interval, 2 has got to be the absolute min. Has to be. Why? Because we start at some y value at 1. We decrease our y values until we get to the y value at 2. And then we increase our y values from 2 to 3. 2 has got to be the absolute min, just by looking at the signs of the derivative. So if I just asked you to find the absolute min of the function, you could have used this as your kind of justification. That f decreases from 1 to 2, increases from 2 to 3, boom, absolute min. You didn't have to find the y values. Sometimes it's easy to find the y values. Sometimes it won't be easy to find the y values, and this is actually quicker. So this is definitely the absolute min using our first derivative test, which we learned in Unit 4. But if the question was to find the absolute max of the function, could I use this and know definitively that it's going to be at 3, not at 1? No, definitely not, because you don't know where you start. You just know you decrease and increase. You don't know how much you decrease. You don't know how much you increase. You don't know if this is going to be higher than this. So if I ask you to find the absolute max, at least you know it's not going to be at 2. You would just have to look at your candidates at 3 and at 1. And then you would say at 3, it's definitely 5. Does that make sense? So we're kind of combining our knowledge from Unit 4, and we're also combining the fact that we know absolute maxes and mins will be possibly at endpoints or these relative extremes.
So basically what you just proved is that the absolute max on an interval won't necessarily be the absolute max of the function.
Yes. I mean, this is 0 is not the absolute max of the function for this.
Yeah.
It's not necessarily what I proved for this. This is just, applying this extreme value theorem for this function on this interval. Okay? All right. Let's do another one. So we got a particle that has a position function given by that. And the question is, what is the particle furthest to the left? Okay, we're kind of working our way towards what the second half of this lesson will be. And the second half of this lesson will be optimization, which is maxes and mins for real world scenarios. Not yet. These all are optimization questions. Finding a max and min is optimization. But in terms of like the real world problems that we're going to talk about, we're not there yet. So this is pretty real world. Anyways. If I'm talking about position, we know we really just talk about one-dimensional position, moving right, moving left, moving up, moving down, one or the other situations. We're trying to figure out when a particle is furthest to the left. Okay? If this is my position and I want to figure out when I'm furthest left, well, this location is going to be a min. When am I furthest left? When we have an absolute min. For my position function. Now, to find a min of a position, what should we do? Take the derivative, set it equal to 0. Pretty much every single question today, you're going to take the derivative and set it equal to 0. Whenever you're asked for maxes and mins, take the derivative, set it equal to 0. There's two tests that you can do. You can do the first derivative test and look at your signs as your first derivative, or you can go straight to the candidates test. It's up to you. A lot of people, once you kind of pick your version, you stick with it, but it's good to be able to go back and forth between the two as needed. It's probably best to start with this one and then go to this if we need to. X prime is going to be negative then positive. By looking at that, I know that when t is 1, that is definitely going to be my absolute min, which is when we are going to be furthest left. How do I know that? Because we start at 0, we decrease in our position values, and then we get to 1, and then we increase in our position values. That's got to be the absolute min. So I don't need the candidates test, really, if I just look at the derivatives. However, if the question was not when are we furthest to the left, if the question was when are we furthest to the right, all of a sudden I can't use this anymore. I can't answer definitively if it's 0 or 2. I have to compare. So figure out these values as well if you haven't done so already, to figure out when you're furthest left and when you're furthest right. (16 minus 12 is 4, plus 2 is 6. So 2 is when we're furthest right. Okay, any questions about that? Okay, one more example before we get to true optimization questions. The question you see sometimes on the AP test, they talk about finding the maximum vertical distance between two functions. So two functions, 9 minus x squared. 9 minus x squared looks something like that. X squared minus 8x looks something like that. At a given x value, they will have a vertical distance. Trying to figure out when the vertical distance between the two functions is the greatest. Now, to figure out when we have the maximum vertical distance, we're going to have to take the derivative of whatever this distance expression is and set it equal to 0. Right? That's how you find a max or min something. What is the something first? Take the derivative of it, set it equal to 0. Well, how do I find kind of this distance between my two functions at a given point? Ms. Floyd?
Could you take the derivative of each and find the maximum point interval between them?
That's a good idea. So you find the maxes of both of them. But what if the max on one is different from the min on the other? Then that would be kind of like a diagonal distance. That would probably be the max distance between the functions overall, but we're talking about on a straight line going up and down. I like the idea, but that would be kind of diagonally. Miss Anarino?
Actually, I don't think this would work. I was going to say the max on one and then of the other, but that wouldn't necessarily work because they could be just like the side.
Exactly. Mr. Obregon? Right. So that would be the expression of just my distance. The top y value minus the bottom y value. If this was at 2 and this was at -3, this distance is 5, right? Well, that means our vertical distance can be expressed by this. Top x value, the top y value minus the bottom y value. Subtract the two and you'll find your distance between them. I want to figure out when that's a max. How do I figure out when that's a max? Take the derivative, set it equal to 0. Everybody do that for this. Maybe simplify it first before you do that. Yep. Oh. 9 is 0. I get x equals 2. Just by getting x equals 2, can I say for certain that that's going to be the max distance between the two? No. What should I do? What's one thing I could do to make sure that is the max? We can do a number line. Boom. So all of a sudden we can do a number line. What's another way, Mr. Griggs? Exactly. Either way, hopefully one way will show you, but if one way doesn't show you, the other way will. We go from 0 to 4. We're looking at 2. I plug in something like 1. This is going to be positive. I plug in something like 3. This will be negative. Boom. I don't need to do the candidates test because I know for certain that is going to be the absolute max. But we could check x of 0, x of 2, x of 4 to find out that this distance at 2, 9 minus 16 times 2 is 32. 9 minus 32 is negative 23 plus 16, 7. And then at 0, the distance is 9. Wait, I made a mistake. 17, I was off by 10. 17, at 0, this is 9. At 4, I believe it's also 9. Okay, so turns out we have 2 absolute mins at your endpoints there, and that 2 is definitely the max. Okay, this would be the minimum distance, vertical distance between 0 and 4. There are no other distance that would be smaller than this. We know that because D is going to increase until 2 and then decrease until 4. Okay, so that's another kind of example of finding maxes and mins. We got to kind of set things up, take the derivative, set it equal to 0. Now let's work into optimization questions. So you don't have to write all this down, just pay attention. We're going to find the largest or smallest value of some quantity that will fulfill a need. Like we want a certain amount of space in a house, but we want to use the least amount of material. We want to find the fastest route. Here's the key. We're going to produce two equations. One is going to be optimized. Whenever you want to optimize one, again, take the derivative, set it equal to 0. And the other one is going to be your secondary. We call that kind of like our fixed relationship, which we've used before, or our constraint. We will solve this one for a variable, plug into the other. Let me show you an easy one. We got two positive numbers, x and y, where the product has to equal 192. We want the first number plus 3 times the second number to be the smallest possible out of all of these situations where we can have two numbers multiplying to equal 192. Now, we're not just talking about whole numbers. We have an infinite collection of points that are positive that multiply to 192. So you can think of, sure, 1 and 192, that's a possibility, right? But you can have root 192 and root 192. That's also a possibility. Any two numbers, as long as they multiply to 192, they're a possible solution, right? But the key to this is that the first number plus 3 times the second one is a minimum. Now, in the past, you guys would try to probably guess and check to see which one would give the smallest x plus 3y. Now we will use calculus. We will not guess and check. So I'm not even going to write down possible solutions. Instead, we just kind of understand that we have a fixed relationship. What is our constraint? Or it's our fixed. And then we have what we are trying to optimize. Sometimes you set this equal to something. Other times you don't have to. I'll show you why. This is a kind of a sum, so I'll say s is equal to x plus 3y. Sure. I want to optimize that, and I'm given that. Now, let's do it without the s. When you're trying to find the max or min for this, you would take the derivative and set it equal to 0. The problem is you have x's and y's. That becomes difficult to work with to set equal to 0 and to solve. However, I have a relationship between my x's and my y's. X times y has to equal 192. I can solve for one of these two variables. It does not matter which one you solve for. You can solve for x, you can solve for y. Let's just solve for x. We can put that into my optimizing equation. And now we can take the derivative of this and set it equal to 0. Now, if you used s, the sum is equal to, and you took the derivative of s, first of all, you're thinking, oh, I have y's. Do I have to, have dy dx? No, we're not trying to find tangent slopes here. We're just trying to find the maximum or minimum y value. You're going to take the derivative with respect to whatever variable you have. I will take the derivative with respect to y. And instead of like ds dy, I can just say s prime. Or I just don't even have that at all, because I know once I take the derivative of the right side, I'm going to take it and set it equal to 0. Now this is y to the negative first. So the derivative of 192 y to the negative first is negative 192 over y squared. And this is plus 3. That's the derivative. Set it equal to 0. And then solve. I get y squared equals 64. That means y has to be positive or negative 8. Well, is it positive or negative 8? just positive. I just found y, find x by plugging y back into that constraint equation.
Did you just skip the process of like doing the derivative of 192 over y? Because that's what it simplifies to.
Yes, so it's 192 y to the negative first, so it's negative 192 y to the negative second. I didn't use the quotient rule. Remember, when you have the y in the denominator, it's not 192 over dy prime, it's y to the negative first, negative 192 y to the negative second. Simplifies to that. Plugged it back into this kind of constraint equation, xy equals 192. Because in the question it says find the two positive numbers. Okay?
Wouldn't it have been 192 equals negative 3y squared?
It's negative 192 equals negative 3y squared.
Oh, so you just
Yep. So it turns out of all of the possibilities, all of the two numbers that multiply to be 192, when you have 8 and 24, that will give you the minimum this, x plus 3 times y. So that's 24 plus 24 is 48. That is the minimum sum of those two numbers out of any other possibility. Try another one. 1 and 192, it'll be bigger. Root 192 and root 192, it'll be bigger. Okay? Power of calculus.
Why did we only go with possibility? Oh,
It's okay. All right, you guys try. Well, you want a max. So we want positive numbers. No. Don't forget to take the derivative and set it equal to 0. A lot of times we substitute stuff in, and then after we substitute and simplify, a lot of people like to set that equal to 0. The crucial step is to actually take the derivative. I almost forgot. All right, we get 25 and 50. No matter which way you did it, if you solved this for y and got 100 minus x divided by 2, you would still get the same answers as I did. Okay? All right. Now, those are the easy ones because the equations are given to you. You might be given situations where you have, a situation where you will be able to produce the two equations, one that you're going to take the derivative and set it equal to 0, the other one that's going to help you simplify the first one. But you got to figure out the two equations from the information in the problem. So we have a gardener who wants to make a rectangular enclosure using a wall of a barn as one side and 120 meters of fencing for the other 3 sides. We want to find the dimensions of this rectangular enclosure that would give us the greatest area. It's very important to use variables for unknowns. I don't know what the dimensions of this rectangular enclosure is going to be, but I know it's got to have a length and a width because it's a rectangle. So I say I got x, x, and y. Tight squeeze over here. Question says, find the dimensions that give the greatest area. Well, area is xy. This is what I want to optimize. X times y. What is my constraint? The amount of fencing that I have. I only have 120 meters of fencing. So, x plus y, 2x plus y is my constraint. Equaling 120 is my constraint. My fixed relationship. Once we got that down, solve one of them, solve the guy on the left for one of the variables, plug it into the other one, take the derivative, set it equal to 0, solve. We get 30 for our width and 60 for our length. Okay. Next problem. We have a square piece of material, and we are making an open box with a maximum value from that square piece of material. The material is 36 inches on each side. And how we're going to do it is we got this square piece of material, we're going to cut equal size squares from the corners. And we'll be able to kind of flip up the edges to make a box. You can kind of see the box once you draw some dotted lines here. This is going to be the bottom, the base. And these little flaps are going to be folded up to be the sides. Now in this situation, the constraint is the picture that you drew. I'll show you why. And we want to maximize the volume, which is for a box, length times width times height. Okay. Well, I want to rewrite that equation for the volume of my box given this constraint, this picture. Now, what is the unknown quantity for this picture? The new length of the sides, which is determined by what? Which is determined by the length and the width of the box that you cut out from the corners. So we need to denote this as x, all of these lengths here as x. All right? Well, from one side to the other is 36. What would be the length of the bottom here? Good. 36 minus 2x. So I start by saying, okay, I got this. Now the width would be the same thing. And the height of the box would be determined by that x that gets flipped up. So I get that. All of a sudden, I have an equation with just x's. I can take the derivative, set it equal to 0 to solve. Now, it actually will be easier if you use the product rule and the chain rule here instead of distributing. Let me show you why. So let's use the product rule. We got the derivative of the first. Don't forget the derivative of the inside times the second plus the derivative of the second times the first. We set this equal to 0. Well, I'm not going to distribute again because we have like terms that I can factor. I have two 36 minus 2x's. I'll factor out a 36 minus 2x. I have just negative 4x remaining from the left term. I have 36 minus 2x remaining from the right term. I then can combine my x's over here on the right. And I get my two answers. $18 and $6. Well, are they both maxes? Is one a max, one a min? Which answer am I looking for my max volume? $18, right? The bigger one, you think 18, right? Well, let's think about what happens if I take a square piece of material, 36 inches on each side, and I cut out boxes of size 18 by 18. What would happen? We would have no box because we'd be cutting out all of this, all of this, all of that, and then poof, you have nothing. So this is actually the min. It'd actually be the same as if x was 0. You'd have no box. This would be the max. It can be confirmed if you looked at v prime, starting at 0, 6, and 18. It would go positive and then negative. All right. Good. Last type of question. More similar to the first couple questions that we did rather than the last few optimization questions, but it's a good one. We want to find the point on a function that's closest to the point not on the function. Okay, so there's some point on y equals root x that is going to be closer to 4, 0 than any other point. Okay, so what we want to minimize is this distance. Now this is not a vertical distance, this is kind of a diagonal distance. Just another day. Now, this diagonal distance can be found using the distance formula. We know the distance formula comes from the Pythagorean theorem. It's the square root of the difference of your x's plus the difference of your y's. However, to find the min, we'd have to use the chain rule to take the derivative of this big square root. That's nasty. So really, what's going to be easier is minimizing d is the same as minimizing d squared. If I find the minimum d squared value, I will find the minimum d value, or at least the location of the minimum d value. Okay. Now, we're going to just plug in our information into this formula, take the derivative, and set it equal to 0. But the key is this guy right there. That's an x and a y, right? But actually, I'm not going to write down y because it's not a random y. It's a very specific y. The y will always be the square root of whatever this x value is, right? If we have y equals root x, well, instead of y, I'll put root x. So I can take this information, plug it into this formula, take the derivative and set it equal to 0, and I will find the minimum distance for the specific point in 4, 0. Let me show you. I'll have x and 4 as my x's. I'll have root x and 0 as my y's. You can distribute if you want to. In this case, it's actually not that bad. Take the derivative, set it equal to 0. Turns out, which is fascinating, that it's not at a very whole number or at a specific number, and that it's actually this simple, that when x is 3.5, this point will be closest to 4, 0. There's no point that will be closer to this than that, just by using the power of derivatives. Okay, I will do one more example of that, which you can watch on your video. Your homework is through your book. Question? Great question, Ms. Prosco. I said d squared, I'm taking the derivative of d squared. It's like, don't you have to change that to 2d, like d, whatever? Well, no, I can actually just say it's d squared prime. And I'll find the min d squared value. Okay? So, no, unnecessary to have 2d. Don't worry, you'll rewatch the question on the video and you'll be fine. All right, so what point is closest to x squared and 2.5? So x squared looks like this. 2.5 is here. Well, a point on x on x squared would be x comma x squared. We are going to minimize the distance squared value. I have, let's start with the x's. So let me just write the formula down. It's x2 minus x1 squared plus y2 minus y1 squared. I'll minimize x minus 2 and x squared minus 1/2. Probably going to want to take the derivative of this using the chain rule. Setting that equal to 0, I'm going to distribute some stuff. So 2 times x squared times 2x is 4x cubed. 2 times 1/2 is minus 1. Times 2x is 2x. Set equal to 0. The 2x's cancel. I get negative 4 plus 4x cubed is equal to 0. 4x cubed equals 4. X cubed equals 1. X equals 1. So it turns out when you have the point 1, 1, that point is the closest to 2, 1/2. Okay? Fantastic. That is the lesson. Take the derivative, set it equal to 0.